Hi friends, welcome to Concepts of Geology, the online platform where we are learning crystallography since the last 4 or 5 classes, and till now we have concentrated only on the two-dimensional arrangement of motifs in any given structure. So we have learned the two-dimensional lattices or plane lattices on the last class, and today we will add one more direction and we'll try to find out which basic shapes of unit cells are possible in 3 dimensions. Okay, so for today the topic is this one, okay, the unit cells on 3 dimensions, and the question which we will try to answer after this class is what shapes of unit cells are possible in 3 dimensions. Okay, so let's begin. Now recall, on the last class we have discussed about the 5 basic shapes of unit cells in 2 dimensions. Okay, so they were parallelogram, diamond, rhombus, rectangle and square. Okay, and their corresponding lattices were clinonet, diamondnet, hexanet, orthonet and squarenet. Okay, as depicted in this figure. Now to decipher the 3-dimensional arrangement of atoms or the 3-dimensional shapes of unit cell, we will not use the diamond shape or the diamond net. Okay, rather we will use rhomb and square. Okay, actually these are 2 special forms of a general diamond. In case of a rhomb, the angle sustained between the 2 translation vector is 60 degree, and in case of square all the angles are right angles. So now we will take all the basic unit cell shapes in 2 dimensions one after another, and we will add one more direction to create the 3-dimensional basic shapes of the unit cells. So first think of this clinonet. Okay, here the unit cell shape was like a parallelogram. These 2 translation vectors along a axis and b axis, okay, TA and TB, those were not equal here, and the angle sustained between them was general angle. So now if I add a third dimension, that is the C axis, with a different translation vector, that is TC, which is inclined in a general angle with the basic clinonet, then the created unit cell shape is called, this is called a triclinic prism. Okay, look here, all the translation vector TA, TB and TC, those are unequal, and the angle sustained between them is a general angle. They are not right angle or not 60 degree or 50 degree, whatever. Okay, they are general angle. So this is called triclinic because all the 3 axes are inclined, they are not right angles. Okay, as all the 3 axes are inclined, so the shape is called a triclinic prism. Now here I have a convention to say you that the angle sustained between this A and C is called beta, C and B is called alpha, and A and B is called the gamma angle. Okay, now to remember that I have a process here. Let's look on it. I have written A, B and C in a triangular pattern. Actually these are abbreviated from the translation vectors. Now the angle sustained between B and C vector is called alpha. Okay, now see, this is just opposite to the letter A. Okay, so this is a easy process to remember because A is coming just opposite to the alpha, or the alpha is coming just opposite to the A. Okay, similarly the angle sustained between A and C is called beta, and look here, the beta is coming just opposite to the letter B. Okay, the angle sustained between A and B is called gamma. Gamma is coming just opposite to the letter C. Okay, so you just take this circular diagram into your mind and memorize the convention of this nomenclature. Okay, fine. Now next come to the rectangle or the orthonet. Okay, here the unit cell shape is like a rectangle. So the 2 translational vector, that is TA and TB, here unequal again, but the angle sustained between them is a special angle, that is 90 degree. Now if we add the C axis with the translation vector TC, that is unequal to the rest of 2 vector and inclined in a general angle, then the resulted object is called a monoclinic prism. Okay, here look, the only one axis is inclined and the rest 2 axes, those are TA and TB, is perpendicular to each other. Okay, so that means this is called monocline because here only one axis is inclined. Remember, in case of triclinic we had all the 3 axes inclined. The cell metric is here A not equal to B not equal to C, no vector is equal here, but the alpha equal to gamma equal to 90 degree and B is not equal to 90 degree, it is normally greater than 90 degree. Okay, very fine, monoclinic prism is okay. But in a special case, if the third vector is arranged in a right angle to the basal rectangle, then the resulted unit cell will be an orthorhombic prism. Okay, so look here, this TC is just arranged perpendicular to this basal orthonet. Okay, so here TA, TB and TC all are unequal, but all angles are 90 degree. Okay, so no axis is inclined here. This shape is called an orthonormic prism. Okay, after the orthonet we are coming into the hexanet. Here both the translation vectors were having same length and the sustained angle between them was 60 degree only. Okay, this is a special angle. The shape of unit cell in 2 dimension was called a rhomb. Okay, when we take such 3 rhombs together we get a regular hexagon which shows the optimum symmetry of the lattice, that is a 6-fold rotational axis. Okay, now think of 3 dimension. Suppose a third vector is added just orthogonally to the basal hexagon and the resulted 3D unit cell is called a hexagonal prism. Okay, so this is the basal hexagon and I am adding a perpendicular TC vector to create this 3-dimensional object. This is called a hexagonal prism. Okay, so here the cell matrix is the basal vectors TA and TB were equal, but the perpendicular vector is not equal. Okay, so TA equal to TB but not equal to TC, and here the angular convention is somewhat different. Okay, now keep it into mind that alpha equal to beta equal to 90 degree. Okay, these angles are alpha and beta, but the gamma, which is the angle between A and B, this is 120 degree only. Now next come to the last plane lattice, that was the square net. Okay, here both the translation vectors TA and TB were equal and the angle sustained between them was a right angle. Fine, now I am adding one more translation vector, that is TC, which is just perpendicular to this basal square net pattern, but the length of the TC is different from this TA or TB. Okay, normally this is longer than TA or TB. So the cell matrix is becoming A equal to B not equal to C. Okay, C is this vertical vector and all the angles are 90 degree here. So this shape is called Tetragonal Prism. Keep in mind the base of this prism is a square. Okay, but one more option we may have with this square net pattern. Okay, we may add the translation vector TC just perpendicular to the basal square net pattern, but now the length of the TC is becoming equal to the TA or TB. Okay, so the cell matrix is becoming here TA equal to TB equal to TC and all the angles are right angles. Okay, so this is the maximum symmetric unit cell shape in 3 dimension. Okay, this is a cube. Cubic unit cell is having the highest degree of symmetry. So these are the 6 basic shapes of unit cells possible in 3 dimensions. Okay, and these are the cell matrix. You may take a screenshot of this to remember the basic shapes and the cell matrix. So here I have placed the possible shapes of unit cells in 2 dimensions and the possible shapes of unit cells in 3 dimensions, just one after another, to make a summary of the class. So these are the unit cell shapes in 2 dimensions with which we are adding one more direction to create this 3-dimensional objects or the 3-dimensional shapes of unit cells. But interestingly, after completing the total class, we have something to say mysterious. We have created the 6 basic objects or the basic shapes in 3 dimensions through adding one more vector, but one more shape is there which cannot be created from this 2-dimensional shapes. Okay, this is called a rhombohedral unit cell. We will learn about it after some classes later. Okay, so for now let's memorize this. We have not 6 unit cell shapes, rather we have 7 unit cell shapes in 3 dimensions. Okay, these are cube, tetragonal prism, orthonormic prism, hexagonal prism, monoclinic prism, triclinic prism and rhombohedral prism. Okay, so this is all about for today. Let's meet on a next class. Goodbye till then.